In this video, we're going to prove the lower bound for sorting. So basically, what we want is this. We want to say, what is the minimal amount of work that's necessary to do sorting? Now for us, we've already spoiled it in a sense, right? Because it's a known result, right? N log n is the lower sorting bound, right? We cannot do better than that for comparison-based sorting. But for saying, right, that we don't know what that bound is, right? We don't know that it exists or what it is. So what is kind of the thought process here? In general, if we want to do this for another algorithm. Well, in general, right, we first of all have to have some hope, right, that it does exist. Now there should, so in theory, a lower bound should exist somehow, because the idea there somehow is that if I have some consistency in my computation, right, if I can expect to basically put in a bunch of results, get some result, and be able to time how long they take, and those answers are always the same, well, then I can imagine, well, I'll just put in I could put in all the possible inputs that ever exist, and just see how long does the longest one take to run, right, or something like that, right? There should be some way, right? If I allow myself, right, to have, to test my algorithm on any possible input, right, I should be able to basically find, some bar, right? There should be some bar that exists somewhere that says that, hey, nobody needs more than this time to run. Okay, so hopefully, right, we can assume, right, that it does exist, and it should exist basically for any like real algorithms, algorithms that terminate, algorithms that don't have some sort of infinite loop or anything else that they do. It's a little bit weird. Most should have some sort of lower bound somewhere. So what we want to do in this case, right? So let's say, right, we don't know what sorting's lower bound is. The first thing we would start with is basically look for a way to model the problem, because we have this idea of, oh, a sorting algorithm needs to do this. It needs to take this pool of values with some order functions available and convert them into a new pool where they're in this way where this order is correct, right? Where everything that's less than this is before, greater than is after. Like, we want to have some way to represent that. And we want to have some way to represent that that's independent of a programming language, right? We don't want to link this to Java or C or any other programming language. We want this to be an independent result. We want our result to be on the actual problem itself. And so what we'll do here is we'll use this idea of a decision tree. So a decision tree model of sorting is basically saying we're going to map out all the different comparisons that I need to make to understand what my data looks like. So for any algorithm out there, right, that's doing sorting, it needs to have some way to look at its data and query, who goes first. Do you belong here? Do you belong here? Do you belong here? There's going to be some set of comparisons that must happen. So we want to have some way to represent that. And what we'll do is we'll say there is a decision tree. And the decision tree is basically saying, oh, this algorithm does this, then this, then this, and this. These are basically, it's a way of saying any algorithm needs to ask these questions of your data. Right? It needs to make these decisions based on what your data says to it. Okay? We want to model that generically. The hope is our decision tree basically will span what is called the search space. So the search space is to say these are all the possible answers, right? So these are all the possible ways I can need to reorder my input in order to get a sorted result, right? This is my search space. I want to find what is that one path, right? What is that one set of decisions, right, in that search space that gets me to a position where I know how to sort this thing. Okay, that's what we're trying to explore with that decision tree. All the possible different. So it's like basically what it's doing is it's encoding all the different questions that the algorithm could ask of its data in order to get the final answer for that data. So this is what we're going to spend our most time on, is basically this decision tree model. Now for us, right, we're going to start with a little bit of an assumption. We're going to assume that if I have some array, and we'll call it A, or some pool of data, call it A, that I want to sort, and I'm trying to do this lower bounds proof on, we're going to assume that all the elements in there are distinct. Okay, and this will just save us a little bit of time in terms of drawing this thing out, and it's not going to cost us anything in terms of generality, because we could always like relabel things or whatever. But we're just going to assume, right, that all of our data is distinct. All right, so our first path is basically going to be to talk about a decision tree model, showing kind of a generic way to represent all the decisions the sorting algorithm would make. And then once we've talked about that tree, then we'll talk about how we kind of analyze it structurally and mathematically in order to figure out what is the amount of work that's necessary to explore that tree and to find any possible result in the search space.